In this lecture, we're going to talk about what we call the alternating series test. So, alternating series test. In short, we call AST. So, what is an alternating series test? So, before we talk about the alternating series test, we need to know what is an alternating series. So, let's write the definition. A series in which terms are alternatively positive and negative. Alternatively positive and negative. A series in which terms are alternatively positive and negative is called a alternating series. Is called an alternating series. Alternating series. So, for example, let's look at this series. So examples. So let's say alternating series. Alternating series. So, for example, if you write a sigma n going from 1 to infinity, negative 1 to the n minus 1. This can be anything pretty much. It's going to give the sign 1 over n. So this is an alternating series. Let's write the first few terms. So in the alternating series, you always going to see that negative 1 to the power term, because that's going to change the sign. But make sure that the sign changes every time. Positive, negative, or negative, positive, negative. It doesn't matter. The sign has to change. So if you write the first few terms, and if you plug in n equal 1, you get negative 1 to the 0, that is 1. So you get a positive sign, and 1 over 1, so it is 1. And then when you plug in n equal 2, you get negative 1 to the 1, so which is negative, and so 1/2. When you plug in 3, you get negative 1 to the 2, that means positive, and 1 over 3, and 1 over 4. So you're going to see that that's how the term behaves. So if you write the general term, so it is negative 1 to the n, 1 over n, that's the general term. And then, so it's going to go like that. Okay. But later, we can show that, that's the goal of this one, we can show that this series is going to converge. This series going to converge. Now, let's look at the absolute series. What's absolute series means? You're going to consider the absolute terms instead. So that means we can write this one as sigma n going from 1 to infinity. We take the absolute one, 1 over n, absolute. So we just take the absolute value of the term. That means the negative 1 n gonna goes away. So you simply get 1 plus 1/2 plus 1/3 plus 1/4, like that. So the general term looks like 1 over n now, and you know that this series diverge. This is a harmonic series. So this one diverge. This one diverge. So that means there's a slight change make a big difference. So if you look at the alternating series with the plus minus sign, it's going to converge. That we're going to show. We don't know that yet, but we're going to show that. That's the first example of this section. But if you look at the absolute values, you know that the series can diverge, because that's a harmonic series, or there's a p series, p equal 1. P series is p equal 1, so that's going to diverge. So you can see that the behavior is kind of different. So let's look at the what we call the alternating series test. So before we do that, we're gonna need some notation. So what we're trying to do, and the notation, you can say any alternating series, any alternating series can be written as sigma n going from 1 to infinity. So there will be something to talk about the negative sign. So it can be negative 1 to n minus 1, n plus 1, a lot of options. So let's put something. Okay, so it can be n minus 1, n plus 1, or something else as well. And then what you're gonna do, you're gonna take the term, we're gonna call it bn. So that bn is the positive part of this one. So the first part gonna talk about the sign, and then we pull out the, so this one gonna be plus minus, and then bn is the number. So for example, in the previous case, bn is 1 over n. Okay, so so we write it. So in the previous example, bn equal 1 over n. So you can always do that. You can just pull out that term and then you can call it like bn. Okay, so they have a sign and the term. Good. Now let's try the what we call the alternate series test. So here it is. So it's a theorem. This is what we call alternating series test. Series test, or AST in short. So what it says that, so we have a series sigma n going from 1 to infinity, negative 1 to the, let's say, n minus 1, so that now it's positive bn. So that's your series. So this is simply b1 minus b2 plus b3, like that. And we assume that bn is positive, because when you select it like that, bn is positive. Okay, or it can be 0 also. Bn is like that. Let's say it's positive. So then two things can happen. The first one, the limit of bn, so the limit of bn, when n goes to infinity, has to be 0. The limit of bn, n goes to infinity, has to be 0. So the interesting part is, if not, if the limit n goes to infinity, bn not equal to 0. Not equal to 0 means does not exist or something else. Okay, not equal to 0 means it does not exist or some other number. Then the series diverge. So in this case, the series diverge. That's the nth test for divergence. So this is the we learned that before, the nth term test. Nth term test for divergence. So it's gonna apply here. So if the limit does not equal to 0, then we stop right there. We're gonna say, okay, series diverge, we're done. But if it is equal to 0 and one more condition satisfies, the second condition is the bn is decreasing. That means so the bn is decreasing. Bn is decreasing. That is bn plus 1 is less than or equal to bn for some n, after some n. Okay, so we don't need that at the beginning, somewhere after some term. So what we normally call eventually. So at the beginning we don't worry what's going to happen at the beginning, but after some n, everything gonna decrease. If those two conditions are satisfied, so that means bn, the limit of bn equals 0, and the bn is decreasing. If that is the case, then what's going to happen? Then the series converge. Then the series converge. then the series converge. It's very important. And the error when approximating the series by the partial sum Sn, the error when satisfies, so that's the error we normally call Rn, that satisfies the absolute value of this one is simply S minus Sn, that's the error. It is less than the first missing term, so Bn plus 1. So that's a very powerful result. So that's the first missing term. So it says that the error is less than the first missing term, because you know that Bn positive, so we can write like that. So yeah, so this is what we call the alternate series test. It's very easy to use, and also very easy to remember. So what we're trying to do, we're going to check whether the Bn, the limit of Bn equals 0, and also we check whether the Bn is decreasing. So if limit is 0 and Bn is decreasing, if those two conditions are satisfied by the alternate series test, it's going to be, the series going to be converged, the original series converge. And in the case the limit not equal to 0, by the nth term test, the series has to diverge. So let's look at a few examples now. So you can see it's like a very powerful result, and it's very, very useful. So so as the first example, let's try to look at the alternating harmonic series. So that's the first example. So example number 1. Test for convergence. The first one is sigma n going from 1 to infinity, negative 1 n minus 1 or 1 over n. So in this case, you can see that the Bn is 1 over n, and the two tests. What are the two tests? The limit n goes to infinity Bn, which is limit n goes to infinity 1 over n, but we know that this goes to 0. The first test passed. Let's look at the second one. What's the second one? Decreasing, but note that 1 over n plus 1 is less than or equal to 1 over n. So 1 over n plus 1 is less than or equal to 1 over n. That means Bn plus 1 is less than or equal to Bn, in this case for all n. Okay. So thus Bn is decreasing. So therefore by the alternating series test, sigma n going from 1 to infinity, negative 1 n minus 1 Bn converges. So it's very easy to show that this one converges. So this is the first example. You can see that this that easy. Okay, very clear. We check the two conditions. So let's look at the next example. B. How about this one? Sigma n going from 1 to infinity, negative 1 to the n, 3n over 4n minus 1. So what is Bn here? In this case, Bn equal 3n over 4n minus 1. We ignore the sign part. That's the Bn. We simply ignore the sign part. So let's look at what's going to happen now. So let's take the limit. Limit n goes to infinity, Bn, which is limit n goes to infinity, 3n over 4n minus 1. This is a infinity situation, so you only need to worry about the largest term of the numerator and the largest term of the denominator. That's it. We are not going to do like dividing by n anymore because we are advanced now. So we only need to worry about the largest term of the numerator and the denominator. And then you can see that if you go 3n or 4n, so limit is 3 or 4. So which is not equal to 0. Which is not equal to 0. So it doesn't go to 0. Okay. So not equal to 0. So that means by the nth term test, series diverge. So by the nth term test, series diverge. Series diverges. So we're done. We don't want to do anything. Just series diverge because it doesn't go to 0. It just go to 3/4 of Bn. But if you look at the actual term, yeah, I want to tell you something here. If you look at the actual term, so what's the limit of the -1 n over 3n over 4n minus? This is not equal to 3/4, right? What do you get? Because it's the number go to 3/4, but there's a sign change, so it's a fluctuating between the two. So the limit does not exist. So the limit does not exist. So yeah, so there's a slight difference between the two. So the n term test had two versions. One version is you directly take the limit, and you can see that limit does not exist. So from that you can say it doesn't converge or diverge. But if you look at the alternate series test, in the alternate series test we only have Bn. We only need Bn. So if you look at the Bn, so this is the alternate series version. So this is the AST version. In the AST version, you can see that we only need Bn, but it is 3/4 now. The limit exists by 3/4, so but it's not equal to 0, so diverge. Okay, very clear. So let's do another one. See, but this one limit n equal to n going from 1 to infinity, -1 n plus 1 n squared over n 3 plus 1. Okay, so so if you look at this one, what is Bn? Bn is n squared over n cube plus 1. So let's look at the steps. So the first one, the limit n goes to infinity Bn, which is the limit n goes to infinity n squared over n 3 plus 1. So in this case we again need to worry about the largest terms only. So if you look at the largest term, this is exactly similar to the limit n goes to infinity. If you look at the largest term, you can simplify, become 1 over n, so which is 0. So that one passed. So the limit goes to 0. And so let's look at the second step. So the first step is passed. So we normally take that step first, because if it is if it violates, then we don't want to go to the second step. Now what do you want to do? We want to prove that this series the Bn is decreasing. But you know that the Bn in the limit, Bn looks like 1 over n. Bn looks like 1 over n. So it's clear that Bn is decreasing, because when n gets larger, these terms almost looks like 1 over n. 1 over n is a decreasing function. This has to decrease. Okay. So you can say clearly Bn, that is n squared over n 3 plus 1, this is almost like 1 over n, because 1 over n looks like 1 over n, decreases. But if you want to prove it, how to prove it? Okay, so let's see how to prove that. How to prove? What we can do, we can consider the corresponding function. In Calc 1, we remember a technique called, we look at the derivative. If the derivative is negative, this has to be decreasing, so we look at the derivative. So but this is a quotient, so you have to use a quotient rule. So the u over v is a v u prime u v prime over v squared. That's the quotient rule, so let's use that here. So if you use the quotient rule, so you're gonna get, so this is f prime x, so we can use the quotient rule now. So it is x3 plus 1, take the derivative, so we get 2x minus x squared, take the derivative, 3x squared over x3 plus 1 squared. Now you can simplify the top. If you simplify the top, you're gonna get what do you get? 2x minus x cube. So if you pull x out, you're gonna get 2 minus x cube over x3 plus 1 squared. Now you can see that when x gets larger at one moment, let's look at the graph of x cube. X cube looks like this, a cubic graph, so it's going to go like that. So at one moment it's going to pass the number 2. When it's going to pass? When it is cube root of 3. Right after it's passed the cube root, is y equal x cube graph. Right after it's passed that value, this is going to be negative. So this is going to be negative. It's going to be negative. This is negative for x greater than 2 cube root. Okay, so 2 cube root is more than 1. So that means if you pick 2, that's kind of gonna work. Okay, so you can see that. So that means negative. So the derivative negative means the function has to be decreasing. So we can see that. So so therefore, okay, so therefore if f x hence bn is decreasing for n greater than or equal to. So that means the second condition also satisfied. So by the alternating series test, sigma -1 n plus 1, n going from 1 to infinity, n squared over n3 plus 1 decreases. I'm sorry, converges, not decreases, converges. So if it is clearly obvious, you don't want to do all of these. Look at the dominating terms of the numerator and the denominator and write the what we call the asymptotic function. This is what we call the asymptotic function. So so write the asymptotic function. Asymptotic function. Just write the asymptotic function that you can consider. You can get just considering the numerator and denominator. Largest numerator and denominator, and that's going to tell you, because it looks like 1 over n, but 1 over n is a decreasing function, so that means bn has to decrease eventually, not at the beginning. After for large n, this is what happened. So I mean that would be enough if you at least mention that. That's actually clearly say that you know what's really going on there. Okay, so that proving that using derivative is optional, but you need to at least mention that part, the asymptotic part. Okay, so we use that tilde notation for the asymptotics. Okay, so so that's about that. So that's the end of these series problems, but I'm gonna just give you like another idea, but we don't do anything.